So for this lecture, I just wanted to recapitulate all the formulae we needed to go ahead and analyze this pump. There were lots of formulae and how we went about, using them and make sure we know which ones we need. So the first thing we needed was the inlet velocity, the normal velocity at the inlet. And that normal velocity at the inlet to the blade region or the impeller region of the pump was U1, which is the blade tip speed, times the angle of that blade. So those are parameters of the pump, obviously. The blade angle we're given usually, or we could be designing for that blade angle. And U1 is dependent on the angular velocity of the shaft and the inner radius of that blade rotation. So that's how you would get your normal velocity. The water horsepower we can find using density, volumetric flow rate, and U2 times the tangential velocity at the outlet minus U1 times the tangential velocity at the inlet. But we found our model assumes that there is no tangential velocity inlet. We set that equal to 0. That is why this is the only inlet velocity, the normal velocity. So this term goes to 0 here. So you're left with that the water horsepower is just equal to that density times the volumetric flow rate times U2 times the tangential velocity at the outlet. In order to find Q dot, we can use the normal velocity at the inlet times the area of the inlet. So the area of the inlet surface, the inlet to the impeller or the blade region, is equal to the normal velocity. The area is equal to 2 pi times the radius, the inner blade radius, times the thickness of those blades. So you can easily calculate the volumetric flow rate once you have the normal velocity of the inlet. That allows you then to calculate the water horsepower if you have VT out. We showed that we could find VT out. VT out was equal to U2 minus Vn out divided by the tangent of beta 2. So this was another very important formula we derived, which was allowed us to find the tangential velocity at the outlet based on the normal velocity at the outlet divided by the tangent of beta 2 and the tip speed of the blades at the outer circumference. So this is the tip speed at R2. In order to find Vn out, we use conservation of mass, which basically insists that the volumetric flow rates be equal. So we know that the area of the outlet surface times the Vn at the outlet has to equal our volumetric flow rate. And the volumetric flow rate has to remain constant from inlet to outlet. So Vn at the outlet is equal to whatever that volumetric flow rate is divided by 2 pi times the radius of the outer blades, the outer edge of the blades, times the thickness of that. So that lets you get Vn out, and that therefore lets you get Vt out, which you need because you need Vn out to get Vt out. So that lets you get Vt out. Once you have Vt out, of course, then you can get the water horsepower, as we already showed. Once you have the water horsepower, you can get the net head, because the net head is equal to water horsepower divided by rho g and volumetric flow rate. And finally, pumps have efficiencies. The pump efficiency is the water horsepower divided by that amount of energy required to drive that shaft. So the torque times the angular velocity, or another way of thinking of that is the water horsepower divided by the brake horsepower there. All of this, of course, is an idealization. Real pumps have other issues. The fluid doesn't always enter perfectly normal to the impellers. There can be viscosity losses all throughout the system. So this is definitely an idealized model of pumps, but we have been told that this type of analysis generally is accurate to within about 25%. So if you do need to basically design a pump from scratch or to analyze a pump that you have access to get some sense for how much pressure it can deliver, how much volumetric flow rate it can deliver, or how you might change it to increase those things, this type of analysis can be very useful.